Hey viewers, myself Syed Mohammad Saif. Welcome to my channel Guys in Science, and today's topic is relativity and magnetism. Some of you may have think that the relativity and the magnetism like charge, volume, mass and energy and time is a fundamental quantity and cannot be disproven or proven by any means. But that's not the way. The relativity has some rules by which we can prove and define magnetism with respect to the charge and charge with respect to the magnetism. Though the magnetism is a very complex phenomena, the charge itself is essential to define magnetism. Therefore, we always define magnetism with respect to charge using relativity. Before getting into it, I would like to define you some more concepts and you would like to learn it, like Lorentz transformation. Lorentz transformation says that when a body is moving with a higher velocity with respect to another velocity, then it tends to contract in the frame of reference of the body with lower velocity, or the body with lower velocity will contract in the frame of reference of the higher velocity object. So that's it. So how it defines the magnetism using the charge? It's a very simple phenomena, and using just only the Lorentz transformation and relativity we can define the whole magnetism. And also why the moving charge with a constant velocity produces magnetic field but the charge at rest does not produce magnetic field. So let's get into it. First of all, let me consider the example of a current carrying conductor. Because the current carrying conductor can produce magnetic field and can interact with the magnetic field of a moving charged particle, positive or negative. So let's see how it's going. Suppose a positive current carrying conductor from here to there is flowing infinite, and suppose here is a positively charged particle Q, and suppose the flow of electron from this wire is from this direction to that direction. That means the flow of current is in my direction. I don't know why the flow of current is opposite to the flow of electrons, but that's how we learn it. And now, if the electrons were moving in the wire with a velocity of v in that direction, and here the body is at rest, so the electrons are flowing in the wire with the velocity v in that direction, and here is the positively charged particle. Now, if the positively charged particle is here and in the wire, since both are moving relative to each other, that is the electrons and the positively charged ions in the wire, so the density, positive charge density and the negative charge density are equal to one another, because in the frame of reference of each other they are moving relative to one another, and therefore Lorentz transformation will arise, but they will cancel because they are in the frame of reference of the one another. Then how the paradox arises? It arises due to the relative motion of the positively charged ion with respect to the positively charged particle. And we can move a positively charged ion or positively charged particle that should trigger a positive relative motion between the two particles. What does that mean? Let me explain. Suppose if the positively charged particle starts moving in that direction, the direction of the current, the direction of electron with the same velocity v. And now in the frame of reference of the wire or the positively charged ions, the electrons and the positively charged particle are moving in the same direction with the same velocity. It doesn't make any sense now. Then how does it make sense? It makes sense in the frame of reference of the electrons or positively charged ions. In the frame of reference of positively charged ions and electrons, the positively charged particle and the electron is at rest, and the wire and the positively charged ions placed stationary in the wire are moving with a velocity v in my direction from there to here, and therefore Lorentz transformation. When a body is moving relative to another object, then it tends to contract, and then the positively charged ions are moving with the velocity v, then it tends to contract, and when in contract it leaves space in between, and because of that space a null charge, that means there is a decrease in the positively charged density, and since the negative charge density is at rest in the frame of reference of the electrons, in the frame of reference of the electrons or positively charged particle, there will be a lack of positively charged density, and negative charge density will held constant, and therefore a total negative charge density will arise. And as the electrons are moving at the same velocity and the same direction with the positively charged particle, the positively charged particle will tend to attract towards the wire because of the net positively charged particle. And now we can state why the magnetism and electricity is the two sides of the same coin. That's because if we see from the frame of reference of the wire and the positively charged ion, it seems to be electric field, and it's electric field. But if we see from the frame of reference of the positively charged ion or the electrons, it's electric field. Though they are the same forces applying on the same object, though they are in the different frame of reference, because the frame of reference arises the different types of fields. So the different types of fields can be manipulated and stated as electromagnetic field, and therefore electricity and magnetism are the two sides of the same coin. Thanks for watching. Make sure to like, subscribe and share this video. I'll be back next week or Sunday with another video, and thanks for watching. Thank you.